Good morning. Today's is the last lecture, and it's on monolithic materials. So I have three case studies of different monolithic materials, all basically castables. And before you can do a thermal shock test on a castable, you have to dry it out and dehydrate it, and possibly fire it. So it basically ends up being a fired or sintered brick shape, where they start out as castables. So the first one here is the low displacement curve of steady state crack propagation, an interesting source of information for predicting the thermal shock damage of refractories. So these people are trying to derive some additional information off of a work of fracture curve. So the work of fracture surface energy we discussed, it's an important variable for predicting thermal shock damage. Basically, the higher the work of fracture, the better the thermal shock damage resistance. And the area under the low displacement curve is used to calculate this work of fracture, whether it's a chevron bend bar or a wedge, splitting wedge block. It's the area under the low displacement curve. So when these people looked at the low displacement curve, they picked some other points off this curve that might give more information on the thermal shock resistance. So they looked at the value of the tangent at the inflection point on the low displacement curve during the crack propagation portion, and they correlated to experimental thermal shock damage, which was basically the ratio of strength after and before the thermal shock cycle. So R4 prime is the work of fracture times Young's modulus divided by the fracture strength squared. So R4 prime is directly proportional to E over sigma F squared. And this term E over sigma F squared is proportional to the inverse of the stored elastic strain energy. It's basically the inverse of the stored elastic strain energy. So R4 prime compares the energy needed to create crack surfaces to the stored elastic strain energy in the material. So for a brittle material, the stress strain curve looks like this. This is stress versus strain, linear to failure. The fracture strength is sigma F, and epsilon F is the strain at failure. So epsilon F equals sigma F over E. So the area of this triangle becomes sigma F squared over 2E. So the thermal shock resistance can be improved by increasing the fracture surface energy or decreasing the stored elastic strain energy. So this is a typical work of fracture curve, load versus displacement. So load versus displacement curve for stable crack propagation on a work of fracture type test. So they looked at three different points here: the maximum loading point, F max, the final displacement point, and they're cutting it off at 90% of the load. When the load decreases from F max by 90%, they're cutting it off here. And then the inflection point, which is, they're looking at the tangent of this inflection point, this angle theta. So as this tail becomes longer and longer, more resistance to thermal shock or higher work of fracture, this tangent becomes less steep, and this angle becomes smaller. So the steeper this curve, this tangent is, the more brittle it is, the more shallow this slope becomes, the more, let's say, ductile it is. So I don't particularly like cutting these off because these tails go on for a long time. You know, these work of fracture tests are done with very slow crosshead speed, so a curve like this could take a couple hours to generate. So perhaps that's why some of these are cut off. So the maximum loading point, this F max, is the maximum mechanical resistance against the crack mouth opening. The higher the values of F max, they're associated with higher brittleness and higher levels of stored elastic strain energy. The tangent at the inflection point, TG theta, is the maximum steepness of the load displacement curve after F max. So at that inflection point, you take the tangent. The steeper the tangent line becomes, the more unstable a crack propagation becomes, the least resistant the material would be to thermal shock. And then the final displacement point, Cmax, the last displacement point on the load displacement curve, it is taken as 90% of the F max, the maximum force. Yeah, I like to, when I used to run these, I used to run them out till basically zero load. So the higher the Cmax, the more flexible the material, the higher the flexibility, the more the material can deform without failing, the better the thermal shock resistance. So in this paper, they looked at these 3 points, the maximum loading point, the slope at the inflection point on this portion of the curve as the crack propagates, and then the final displacement point, Cmax. They also came up with their own figure of merit, Rx, and another R parameter, but it's simply F max times C max divided by this the angle for this tangent. So they had 5 different castable compositions. These are all based on continuous particle size grading. That's typically what's used in a castable to allow the material to flow. The other approach would be gap sizing. Gap sizing is good if you're pressing a refractory brick to get high density, but gap sizing is not good for flowability. So a lot of the castables are based on a continuous particle size grading. So the maximum aggregate size in millimeters in the first two, A8 and M8, were 8 millimeters. And in the other 3, A2, M2, and Z2, its smaller top size aggregate was 2.3 millimeters. So the first 2 castables had a total aggregate amount of 73%. The second group here, these 3, had a aggregate amount of 63%. So these were all based on a white electro-fused alumina. So fused cast alumina, very dense material, basically zero porosity. But M8, M2, and Z2 had some, again, electro-fused mullite zirconia material at the mullite zirconia eutectic. So this one, M8, had 35% of the aggregate was eutectic mullite zirconia, and M2 and Z2 had 25% eutectic mullite zirconia. So why did they add the eutectic material? Because the eutectic microstructure is unique. In this system, mullite zirconia, there's no compound formations, there's no solid solubility. So when you're at the eutectic and you cool down, you create this layered type microstructure. So the white here would be zirconia, the brighter phase, and then the darker phase would be mullite. So that creates a high number of interfaces. So that increases the probability of propagating crack to be deflected. So this is a very fine microstructure. These layers are about a half micron in thickness. So this is a crack running through the material. There, you can see there is some deflection at these interfaces. So they're using this unique microstructure to see if it improves the thermal shock resistance. So all of these castables are made at the same water content, 4.8% water. Uh, they have to be heat treated. So they're cured at room temperature. They're dried at 110 degrees C. That removes the physically held water. And then they're sintered at 1450 degrees C. So you essentially end up with a sintered or fired refractory brick at this point. The cement phases dehydrate around 300, 400 degrees C. So that's where additional water comes off. So physically held water comes off when it's dried at 110 degrees C, between 110 and 1450 degrees C, mostly around 300 or 400 degrees C. The chemically held water that comes off the cement is dehydrated. You cannot run a thermal shock test like this on a material that's just cured at room temperature. It's got a lot of water in it. As soon as you heat it up where the cement starts to decompose around 300 or 400 degrees C, you're going to generate steam and these bars will explode or be severely damaged. So you have to remove both the physically and chemically held water before you can do a thermal shock test. And in reality, when you cast the wall in a furnace with the castable, you go through a dry out schedule and you remove the chemically held water and the physically held water. So they did a 3-point bend strength on a typical 40 by 40 by 160 millimeter bars, and they used wedge splitting to get the fracture surface energy on the typical 100 by 100 by 75 millimeter block. And this diagram just shows the detail on the dimensions. It's 75 millimeters thick, and the cross section is 100 by 100 millimeters. And then they're showing the sizes for the different notches. And then the thermal shock was done on the 40 by 40 by 160 millimeter bars. The material was held at 825 degrees C and quenched into water at 25 degrees C, one quenching cycle. And then they looked at damage that occurred during this one quenching cycle with the 3-point bending again. So this is retained MOR versus these 5 different compositions. And M8, M2, and Z2 are the ones that had the alumina zirconia eutectic aggregate in it. So you can see that the highest retained strength were the castables with the eutectic aggregate in it. They also measured work of fracture. The same 3 materials, M8, M2, and Z2, had the eutectic microstructures on the aggregates, and it has the highest work of fracture. So the higher the work of fracture, that correlated with the retained strength. So the highest work of fractures corresponded to the highest retained strengths. They calculated R4 prime. And again, the higher the R4 prime, the higher the retained strength. So there is a relationship between R4 prime and the retained strength. And then they made a plot of 1 over the tangent of this angle. And the higher this inverse relationship, the higher the retained strength. So M8, M2, and Z2 are the ones, again, with the eutectic aggregates. So this is 1 over that angle. So the smaller the angle, the more shallow the slope, the higher the retained strength, the better the thermal shock resistance. And then they took their parameter Rx, and they plotted it here, and then M8, M2, and MZ with the higher um, retained strength also had the higher Rx values. So a lot of these parameters seem to correlate. And this one, I'm not sure why this one was done, but this is a comparison of the maximum um, load in the work refractor test and the maximum strength in the MOR test. And they should correlate. The higher the MOR should have a higher peak on the work refractor test. And you can see that the longer bars are the MOR, and the shorter bars are the maximum load in the work refractor test. And they follow the same pattern. They should correlate. So in this work, the addition of these eutectic materials, the alumina zirconia aggregates at the eutectic composition, improved the thermal shock resistance. And when they looked at this parameter, they put together Rx and then 1 over that angle at the inflection point. It looked like there was pretty good correlation with the thermal shock behavior. So they're saying that Rx, or 1 over TG theta, could be a useful way of looking at thermal shock behavior of refractories. And the advantage is to using Rx, or 1 over TG theta, is that it's all calculated in one measurement. So it's all derived from the one work refractor test, whether it's the chevron notch or a wedge splitting test. You're not measuring strength. You're not measuring elastic modulus. So you're getting everything. You're also not measuring thermal expansion. So you're getting all the information from one measurement. So the next paper, a comparative evaluation of fracture and thermal shock behavior of conventional low cement, ultra low cement castables. So a conventional castable is the oldest type composition. It has fairly high cement content. And there were always some issues with the high cement content, alumina, calcium, and silica present in the same castable gave rise to some low melting materials. So they went to a lower cement material to eliminate the lime. Calcium aluminate cement. The more you decrease the cement, the lower the lime content. So the lower the potential for low melting phases between alumina, silica, and lime. And then finally, ultra low cement castables with a very low cement content. And there are actually no cement castables now that use other materials like a colloidal silica or reactive alumina as the bonding matrix. So conventional has high cement. The low cement has much lower cement, and ultra low cement has very little cement. And that trend was just a decreased low melting phases like in orthite and galenite. So conventional low cement, ultra low cement castables were evaluated for fracture and thermal shock behavior by destructive and non-destructive methods. So there were 2 conventional castables, 1 and 2, a low cement castable and an ultra low cement castable. So the alumina contents are here. These were about 87%. This is around 76, and this is 90. Some of the alumina is from the calcium aluminate cement. And you can see the calcium content was about 5.5 here. That's from the calcium aluminate cement. And then some of the alumina here is not alumina, but it's part of the calcium aluminate cement. So going from the conventional castable, about 5.5% lime, lowering the cement content drops this to 2.31% lime. And then the ultra low cement castable is all the way down to 0.45% lime. So much lower cement content. These two LCC and ULCC have some silica present. I'm not sure how these were added, but these usually added as a fumed silica. So the cold crushing strength goes up as the cement content is decreased. These are going to be denser materials. And then they measure the percent linear change at 1450 degrees C. These three are all around 1%. This one wasn't measured. Measured the thermal expansion coefficient per degree C. And this is around 9, 9, and 9. But the LCC with the highest silica content is around 6.4. This is due to the fact that the silica reacts with the alumina and forms mullite, a low expansion material. So this one with the lower expansion has an advantage over the other three in thermal shock resistance. So they measured properties after drying at 110 degrees C and then firing at 1,000 and 1,500 degrees C. They measured the bend strength, and these are cold properties after firing at these temperatures. The bending strength, the Young's elastic modulus by a resonance technique, and they measured fracture toughness with a single edge notch beam. And that allows you to calculate gamma NBT once you know the elastic modulus. So that's the fracture initiation energy. And they also measured worker fracture, the fracture propagation energy, with the same single edge notch beam. You do not have to use a chevron notch sample if you can get a stable fracture with a straight through notch, like in a single edge notch beam. You can do it that way. If you have trouble getting a stable fracture, you have to switch to a chevron notch configuration. And they measured elevated temperature properties at both 1,000 and 1,500 degrees C after they were fired to those temperatures. They measured bend strength, Young's elastic modulus by resonance, fracture toughness with the single edge notch beam, and a calculated gamma NBT once they measured the elastic properties. So the thermal shock after firing at 1,500 degrees C was done at 1,000 degrees C, and it was quenched in air at 25 degrees C. So from 1,000 degrees C down to 25. And they ran cycles up to 11, usually 9 to 11. It just depended on how well the material performed. And they monitored the damage by both bend strength and Young's elastic modulus. So this is cold MOR, hot MOR, and hot modulus of elasticity. A couple of things to point out. The conventional castables start at about 9 megapascals. At 1,000 degrees C, the hydraulic bonds from the cement are destroyed. The porosity increases. It's a weak material. So the strength falls off to about half its value. And then as you go up higher in temperature, the material starts to sinter and the strength starts to increase. In these low cement castables, you don't really see the strength falling off because of the low cement contents. And then at the higher temperatures, there's sintering taking place and the strength increases. This value is quite high because of most likely of the mullite that's forming in this material. And the hot MORs at 1,000 are somewhat similar room temperature, but when you get to higher temperature and you start forming viscous glasses, the strength really falls off. You can see how it really falls off. This one doesn't fall off as much because apparently there's a substantial amount of mullite needle crystals, those interlocking crystals that improve the strength. And the hot modulus of elasticity, Young's modulus, it gradually falls off as you increase the temperature. So it's a little bit lower at 1,000 than 110 degrees C. This table has the cold fracture toughness, the hot fracture toughness, the hot gamma NBT, and then this is a room temperature worker fracture. So if you look at the toughness values, they're typical of refractories between 1 and 2, and these are megapascal square root of meters. It's a little lower at temperature, especially at the highest temperature. It really falls off, but the strength falls off. And the low Semitic castles are slightly better, but still not very high values of fracture toughness. A little bit higher for the ultra low cement castable. And then the fracture initiation energies in joules per meter squared. It's going up somewhat in the lower cement materials, and especially at the higher temperatures, where the material becomes somewhat plastic, perhaps, maybe some liquid phases are forming and blunting the crack tips. And then the worker fracture is highest for the ultra low cement castable, and it goes up as you increase the firing or sintering temperatures. So at the sintering temperatures, you probably are forming some viscous liquid at these higher, the higher temperature of 1,500 degrees C, making a stronger material, and the work of fracture is increasing, but especially for the ultra low cement castable, it's the highest. And they calculated R3 prime and RST. And these are calculated at temperature. So they didn't have worker fracture at temperature, so they didn't calculate R4 prime, they calculated R3 prime. So at 100 degrees C, R is in a 200 or 300 degrees C range, not very high. And at 1,000, it goes up to a little bit higher temperatures, approaching 500 or 600 for the low cement castables. And then R3 prime does not make a lot of sense here. It starts out low, it increases, that's fine. But in these two, it decreases at the 1,000 degrees C relative to 110 degrees C. And that's because the work of fracture really increased here. If this was R4 prime, this probably would look reasonable. But again, R3 prime does not include the work of fracture. And these are different materials, so they can't really compare R3 prime. And they calculated RST, square root meters degrees C. And in all the cases, as you went from 110 to 1,000 degrees C, the RST values increased and were highest for the low cement and ultra low cement castables. So based on RST, these two castables should be the best in terms of thermal shock resistance, the LCC and the ULCC. Young's elastic modulus, and this is in gigapascals at room temperature. 47, 57, 51, they're all pretty similar, but the ultra low cement castable is denser and has lower porosity, so it has the higher elastic modulus. So the retained bend strength and retained Young's elastic modulus after thermal shock. This is for the conventional castable number one. So retained strength or MOE. So the diamonds are the retained strength, the squares are the retained Young's modulus. They're very similar trends. So this is 0, 3, 5, 7, and 9 cycles. And then this is the percent. So either retained strength or retained modulus after 9 cycles is down to about only 12%. So there was significant damage after 9 cycles. Castable number two is almost the same. It went up to 11 cycles before they stopped the test, and the values were about 20% retained for the strength or the Young's modulus. But they both track in a very similar manner. So this is for conventional castable number two. And then LCC, the low cement castable, which had a little bit better RST value, went out to 11 cycles. The retained strength was about 36%, and the retained modulus was about 30%. So there's an improvement here, less damage, so higher retained strength and higher retained Young's modulus. And then the ultra low cement castable had the highest RST value and performed the best. The retained strength was 54%, and the retained modulus was 66%. So this material performed the best and had the highest calculated RST value. So all four castables exhibited gradual loss in strength. None of these curves after so many cycles dropped off. They're all exhibited a gradual strength or modulus loss. So that indicates that we're in the quasi-static crack propagation region where RST applies. So all four castables exhibited a gradual loss in strength or a gradual loss in Young's elastic modulus with the number of increasing thermal shock cycles. And that gradual loss in properties indicates it was quasi-static crack growth. So large cracks were additionally present, and that's where RST really applies. So RST basically correlated with the thermal shock results. And then the last example I have here is looking at the calcium aluminate cement itself. So they're looking at the effect of particle size of the calcium aluminate cement on the stability and thermal shock resistance of a calcium aluminum cement bonded castable. So the properties of these calcium aluminate cement bonded castables are influenced by the size and distribution of this phase that forms CA6 after sintering. So these castables were the aggregates were corundum or alumina based, bonded with a calcium aluminate cement. So the size and the distribution of the in situ CA6. So this is a phase that forms at high temperatures after the material is sintered, is related to the calcium aluminate cement particle size that you start out with. So they looked at properties of CaC bonded corundum based castables with different CaC particle sizes. So they looked at the demolding strength after curing at 30 degrees C, the drying strength after drying at 110 degrees C, the volume stability, and the thermal shock after sintering at 1450 degrees C. So it's basically an alumina aggregate, and with a CAC cement matrix. So the green strength of CAC bonded materials is obtained by hydration. And these are the different hydration products. And this is in cement notation. Actually, I should have mentioned it here. C is calcium, A is aluminum. So it's CaO, Al2O3, and the Al2O3 is taken 6 times. So this is calcium, aluminum, and H is water. So CaH10 would be CaO, Al2O3, H2O taken 10 times. C2AH8, C3AH6, and AH3. So if you're casting at room temperature, you're going to end up with this phase C2AH8. If you're casting somewhat above room temperature, you're going to end up with C3AH6. And if you're casting on a cold day below room temperature, you're going to end up with CAH10. This is undesirable. You do not want to make it castable and have CAH10 show up. So you don't want to cast at temperatures below room temperature. You can see that this has a lot of water in it. So when this dehydrates, it's going to create a lot of porosity and be the weakest of all these different hydrated phases. AH3 is going to be present in all of these, most likely amorphous below room temperature. So that's just a little bit of background on the phases that develop in the castables when they hydrate. So coarse particle size, CAC, between about 10 and 40 microns, may not completely react with water during this curing process. So what you may see is a reacted rim of thickness about 1 or 2 microns on these particles, even after curing for 24 hours. So the unreacted CAC does not contribute to any development of strength. It's just still unreacted. So if you reduce the particle size of the cement, of CAC, it's a simple approach to increasing the green strength of the castables. It also means that you could probably reduce the amount of CAC and achieve the same desired strength as a coarser particle size CAC. So the reduction of CaO in the CAC cement also reduces the amount of low melting phases. So if you can go to a finer particle size cement with using a lower amount of cement, you're going to decrease the amount of galenite or anorthite. And galenite is C2AS, S is silica, anorthite is CaS2. These melt at about 1590 and 1550 degrees C. So if you're, in a steel application, these are lower melting than where you're going to be melting or refining the steel. So these are undesirable phases. And then when you create calcium hexaluminate, Ca6, that improves the volume, stability, and thermal shock resistance. And this phase will show up after sintering at 1450 degrees C. And this is somewhat similar to the mullite microstructure. Mullite had a needle-like interconnected structure. Those are the crystals of mullite. The crystals of Ca6 are sheet-like interlocked crystals. So that kind of microstructure enhances, in general, will enhance the thermal shock resistance and the strength. So the castables are made with 4.6 weight% water, and the normal size bar is 40 by 40 by 160 millimeters. Cured at 20 degrees C, dried at 110 degrees C, and sintered at 1450 degrees C. So the tabular alumina these are the aggregate sizes: 6 to 3 millimeters, 3 to 1, and 1 to 0, and less than 0.044 millimeters. So all of these four tabular alumina sizes were kept constant: 20%, 30%, 20%, and then 18%. So four compositions: S0, S21, S22, and S23. And then they also had some reactive, very fine particle size alumina. And this one was 7, 9.5, 8.5, and 7. The water content was all the same, 4.6. There was a dispersion at 0.2. And then the cement, was either not ground, that's 0 hours, or ground for 2 hours. So S0, 0 hours, was at 5%. So that's unground, that's the coarsest cement. And then these other three went from 2.5 to 3.5 to 5 on calcium aluminate cement that was ground for 2 hours to make it a finer particle size. So those were the four compositions. And this is the CAC before and after grinding. So unground, 0 hours, the maximum size was 65 microns. 20% was greater than 30 microns, 55% was greater than 100 microns, and 16% was less than 3 microns. The specific surface area and meters squared per kilogram was 446. And then this is the mean particle size in microns, was about 12. And then after grinding for 2 hours, the maximum size was reduced to 10 microns. There was nothing over 30, nothing over 10. 94% was less than 3 microns. The surface area went up to 552. And then the average particle size was down from 12 to 1. So much finer material. So they measured the cold bending strength after curing, drying, and sintering, and also the cold compressive strength. And the linear change for volume stability was measured after sintering at 1450. So the thermal shock was done on samples fired at 1450. So these are well sintered materials. The quenching temperature was 1100 degrees C, quenched into 25 degrees C water, one quenching cycle. And they use both bend strength and the compressive strength to monitor the damage. So this is the cold bending strength and cold compressive strength after curing. So this was at 110 degrees C curing. So the open bars are the MOR, and the crosshatched bars are the cold crushing or compressive strength. So ceramics in general, refractories included, the compressive strength is usually 5 to 10 times more than the bending strength. So they're much stronger in compression than in tension. So you can see the modulus of rupture in MPa is all around 5 or a little bit higher. And then the cold crushing strengths are much higher, from 15 all the way up to 35 MPa. This is after drying. There's a modulus of rupture and cold crushing strength. So I'm sorry, this was after curing, just at room temperature. This is after drying. So this is 40 as the maximum on both vertical scales. This is 100. So after drying, there's some more cement hydration. So they become a little bit stronger. So the cold MOR is a little bit higher, and so is the cold crushing. but there's still the disparity. The cold MR is much lower than the compressive strength. So this is the ratio of cold bending strength or compressive strength after the thermal shocking. So residual cold MOR in percent or residual cold crushing strength in percent. So the black curve is the cold MOR, the blue curve is the cold crushing. So S0, S21, S22, and S23. So this has no ground cement. S21, S22, and S23 have the ground cement, and they're going up in cement content from 221 to 22 to 23. So this material S21 is a much lower cement content than the unground cement content over here. So it has a lower performance. But then as you increase the cement content all the way up to here, S23, you can see that the performance in thermal shock, whether it's monitored by cold crushing strength or cold MR, starts to increase. So going all the way back, S0 had 5% cement, S21, 2.5, S22, 3.5, and S23 had 5%. So this one at 3.5 is getting close to this one at 5, and this one has the same cement content as this. They both have 5%. So it has the finer particle size cement improve the thermal shock resistance. So they ran X-ray diffraction on S0, X21, S22, and S23. And then the aggregate is primarily alpha alumina, the triangles. You can see the large peaks here for alpha alumina. And then this is the sintered material. So the cement phases are gone, and we're forming Ca6, and we're also forming a little bit of Ca2, another high temperature calcium aluminate cement type phase. Ca2 is the squares, Ca6 is the circles. So if you look at this one here, this peak, it's small, it gets larger, and it gets larger. So the amount of Ca6 is increasing as we go from the unground to the finer cement materials. And also some Ca2 starts to appear. So from the X-ray diffraction patterns, the formation of Ca2 and Ca6 occurring as we grind the cement finer and have a higher cement content. These phases, when they form, have a volumetric expansion. So Ca2 is an expansion of 13.6, and Ca6 is 3%. So when you form these smaller sized crystals of Ca2 or Ca6, you're actually creating a lot more micro cracks in the structure. So when you grind the cement finer, you create finer crystals of Ca2 and especially Ca6. And because of the volume expansion mismatches, you're creating micro cracks, and that suppresses crack propagation and increases the thermal shock resistance. They measured percent linear change. This is a before and after measurement after sintering at 1450 degrees C. And these finer ground cement had less volume change. These are still small numbers. This is 0.3%, and these are about half. So they looked at the microstructure of the matrix. These are fracture surfaces of the matrix, a pretty high magnification. The bar is 1 micron. So these were sintered at 1450. And this is the one with 5% unground CAC. And then as you go up, this was one with 2.5 weight percent ground CAC. So you go up in ground CAC content. This is again 1450 for the sintering, and this is the matrix. It's a 1 micron bar. You start to see these sheet-like platelets starting to develop that weren't really present here. There's a few larger ones, but now you're starting to see a lot of these smaller sheet-like platelets developing. And then when you go up to the 5 weight percent ground CAC centered at 1450, you start to see a lot of these platelets of CA6 forming. They tend to interlock in the matrix. So that's giving rise to better thermal shock resistance. So for the microstructure, volume stability and thermal shock resistance of the CAC bonded corundum or alumina-based castables was improved by replacing the cement with a finer particle size. So they replaced the unground CAC with a ground CAC. So going to finer particle size cement increased the thermal shock resistance, and that produced smaller CAC crystals with a better distribution. And that was the microstructures were after sintering at 1450 degrees C. The thermal shock resistance based on residual strength of the CAC bonded alumina based castables was improved with the addition of, again, the finer particle size CAC cements. That increased the microcrack density and increased the amount of sheet-like interlock crystals of CA6. And supposedly they believe that these interlocking crystals increase crack deflection and crack bridging. So that's what I have on castables. Again, castables, you have to remove the water and sinter them before you can do the thermal shock testing because of the steam buildup and steam explosions. So if you have any questions on any of this material, this course was designed to show you how to basically what features in the microstructure, how you can design microstructures to improve the thermal shock of refractories. If you have any questions, you can contact me anytime, and I'll be happy to answer them. So thanks for listening in on this course, all, I guess, 15 lectures, and have a good rest of your summer, and maybe I'll see you in another course. Thanks again.
Thank you.
Thanks.
Thanks, Joseph.
Thanks, Greg. So Greg, have